Hello and welcome to this presentation related to friction belt drives. This is part 1 of the lecture and relates to an introduction to the topic area. Within this first lecture, we will consider basic terminology and nomenclature used within the analysis of friction belt drives, consider various characteristics of belts and belt drive systems, and derive some equations that will allow us to determine the power that can be transmitted in a belt drive, ignoring centrifugal effects. In this part 1, the power transmitted is calculated from knowing the tight side tension in our belt drive and the slack side tension and the linear velocity of the belt. Here's a presentation overview for friction belt drives part 1. This relates to flat belts when we ignore the centripetal or centrifugal effects. We commence with an introduction. We outline applications of friction belt drives, types of belt used, general nomenclature used, such as C for center distance, D for diameter, omega for angular velocity, theta for angle of lap, S for span lengths, T suffix T for tight side tension, and T suffix S for slack side tension. We consider various stresses induced in belts during their operation and consider the advantages and disadvantages of belt drives. Next, we have an analysis of flat belt drives for power transmitted, capital P, with no CF effects considered. We then state some other useful formulae in the analysis of friction belt drives. This relates to belt drive geometric information, such as the span length S, the belt pitch length L, and the angle of lap, theta. We then define the important characteristics of a belt, that's the initial belt tension, T0. We next consider the maximum belt tension, that's TT, and that's calculated from the formula TT is equal to the allowable tensile stress in the belt multiplied by the cross-sectional area of the belt. We calculate the cross-sectional area of a flat belt as B multiplied by D to calculate the area of the belt. Then we consider example 1, where we have to calculate the angular velocity of the pulley, the linear velocity of the belt, the power transmitted, the initial belt tension, the span length, and the belt pitch length. In example 2, we calculate the power transmitted for a flat belt drive with no centrifugal effects considered. And here are the approximate start times related to the various sections contained within the presentation to hopefully aid your ease of access through the presentation. But please note these are only approximate start times. Friction belt drives. Here's a few illustrations. First illustration is from a small grinding machine. The photograph shows the flat belt being driven from the electric motor pulley here, and the driven pulley is shown here. This image in the bottom right hand corner again shows a flat belt that's used in a cross drive. Flat belts are very flexible. In this particular scenario, the direction of the pulleys are reversed due to the crossing of the flat belt. Here's a pillar drilling machine showing the cone pulley arrangement here, showing the belt being driven here on our pillar drill, and driving the cone pulley here, which drives the spindle. Notice this cone pulley arrangement has been used here, which allows the speed of the spindle to be easily changed by simply relocating the belt onto a different pulley set. In this particular case, this would be a V-belt drive. In the top right hand corner, again we show a V-belt drive. This system actually has 3 V-belts being driven by the electric motor, driving our output device or load. And I'm sure you can think of many more illustrations associated with belt drives from your own practical experience, for example in motorbikes, in motor cars, various types of machinery, etc., etc. Let's consider an overview of belt drives. Belt drives are employed to transmit torque between shafts. Where one shaft is doing the driving, termed the driver, is transmitted to another shaft, termed the driven. Belts can be made from a variety of materials, such as leather or rubber, or more commonly these days, a variety of reinforced elastomer materials. There are many types of belt drive in general use, which can include flat belts, V-belts, round or sometimes termed rope belts, and toothed or notch belts. Some of these belts are illustrated within figure 1 on the next slide. Here's figure 1, illustrating flat, V, and round or rope belts. Flat belts usually run on crowned pulleys, i.e. they are slightly convex, as this tends to counteract the tendency of the belt to slip sideways off of the pulley. Just for illustration, here is a typical shape of a crowned pulley, and there are various standards that refer to the crowns for pulleys related to flat transmission belts. So here's the picture of a flat belt running on a crowned pulley. V-belts run in grooved pulleys. Here's our groove pulley. Here's our belt running in the groove pulley. Also note that a round belt or a rope belt also runs in a groove pulley, whilst the toothed belts run in toothed wheels or in sprockets. Just for reference here, symbol beta, shown in our diagrams, relates to what's termed semi-groove angle, and the Rn force shown here is actually termed the normal reaction force. We refer to these characteristics in later presentations. Let's consider flat belts. Flat belts are used mainly for transmitting light loads between shafts. They are flexible and suitable for applications where there is some misalignment between the shafts. Flat belts may be crossed to provide opposite directions of rotations of the pulleys, what's termed contra-rotating shafts here. And flat belts can be twisted to connect shafts which are not in the same plane, as shown here. Applications of flat belts include plant pump equipment, compressed air equipment, heating ventilation systems, air conditioning systems. I'm sure you can think of many more examples yourself. V-belts. V-belts transmit greater power than flat belts as they have increased friction due to the shape. A V-belt can have more than 3 times the grip of a flat belt for the same material. As the V-belt runs in a groove, shown here, it can operate at higher speeds than flat belts, and one V-belt can replace multiple or wide flat belts. Application of V-belts include machine tools, in automobiles, washing machines, tumble dryers, and as already mentioned, pillar drills. Tooth belts, also termed synchronous belts, toothed or synchronous belts, run on tooth pulleys. They give a more positive drive and are used where slipping of the belt would be detrimental to the driven components. For example, timing belts used on automobiles. Synchronous belts have a similar power capacity when compared to V-belts, and applications include drive belt to the camshaft on automobile engines, where slippage can alter valve timing and possibly result in the piston striking the valves. Let's consider friction belt drive nomenclature. So for the scenario shown here, we have our driving pulley labelled A. Left hand side has diameter A, angular velocity omega A. On the right hand side we have our driven pulley labelled B, here diameter B, and the angular velocity omega B. And notice the diagram indicates the typical characteristics of the belt, with the tight side tension shown here labelled TT, and the slack side tension shown here labelled TS. So please be aware of the various symbols and characteristics shown on this slide. We will also make use of the relationship between linear and angular velocity we reviewed in a previous presentation. V is equal to omega R, where V is the linear velocity of the belt, omega is the angular velocity of the pulley, and R is the radius of the pulley. Let's consider stresses that are induced within a belt when rotating. The first type of stress is induced by the tensile force in the belt, which is a maximum on the tight side of the belt, labelled TT in this diagram. That refers to the maximum tension in the belt here. Second stress is induced by the bending of the belt around the pulleys, which is a maximum as the tight side of the belt bends around the smaller pulley diameter, as shown in our sketch here. And the third type of stress is induced by the centrifugal, centripetal forces that occur as the belt travels around the pulleys. In this first lecture we will not consider centrifugal effects, but we will consider these effects in a later lecture. Again, from our previous work, centrifugal forces are considered to be equal and opposite to centripetal forces. But the centrifugal force is essentially a concept we use to bring a dynamic situation into a static situation for analysis purposes. Let's consider advantages of friction belt drives. Belts have several advantages over other drives, for example gear trains. Firstly, they have automatic overload protection due to the fact the belt can slip in service. For example, in a machine shop, if a machine tool experiences an excessive load applied at the cutting tool, the belt has the capacity to slip on the pulley and thus preventing the excessive load being applied to the machine tool and damaging the machine tool. Second advantage, the belts can be purchased in standard sizes from stockists and easily allow for adjustable lengths. 3. Belt drives can be easily geared via use of different size pulleys. For example, we referred to the pillar drilling machine on a previous slide and the use of cone pulleys to allow for different spindle speeds. Item 4. Belt drives allow for reduced noise and so less vibration. And 5. Belts are smooth running. So belt drives are usually employed for driving grinding machines, for example, as there is less vibration and hence less risk of affecting the surface finish. Let's consider some disadvantages of friction belt drives. Firstly, the maximum pulley ratio is generally limited to a 3:1 ratio. And that's because of the limited contact of the length of the belt with the pulley, what's known as the angle of lap, symbol theta. The larger the aspect ratio, the smaller the angle of lap, and therefore the less friction generated, and so the possibility of the belt slipping. And of course, when the belt slips, the transmission of power is lost. Disadvantage 2, repeated flexion of the belt due to the bending stresses we mentioned previously, can cause failure of the belt. Item 3. Small power losses can occur due to slip, creep, and the flexing of thick belts that occurs every cycle. And disadvantage 4. Location problems can sometimes arise related to the use of multiple belt arrangements. As we shown on the previous slide, we can have 3 belts connected together, but sometimes there are problems when trying to install the 3 belts to work efficiently together. Here's some belt drive terminology and nomenclature. The torque is transmitted due to differences in tension existing within the belt when it's rotating. Let's consider the simple system shown in figure 2 here. So again, we have a pulley A, pulley B scenario. In this case, pulley A is the driving pulley. Again, we've labelled the diameter as dA and the angular velocity of pulley A as omega A. I'm also showing here the radius of pulley A, labelled RA, and also the angle of lap of pulley A, denoted as theta A. For the driven pulley, labelled B here, again we have the same approach notation, diameter of the pulley B, radius of the pulley B, angular velocity of pulley B, omega B. Then we have the radius of pulley B and the angle of lap of pulley B. So theta relates to the angle of lap, and that's the angle over which the belt is in contact with the pulley. Note in our diagram that theta A added to theta B equals 360 degrees. Also notice the parameters labelled as C here, that's the centre distance between pulley A and pulley B, and this dimension S, which is actually termed the span lengths between the pulleys. Notice the applied torque is symbol capital T, and this induces tensions in the belt, and for the direction of the applied torque shown in figure 2, this would be the tight side tension and this would be the slack side tension. Be aware that the applied torque would have the unit of Newton meters, but the tight side and slack side tension would have the unit of the Newton. We will now use this terminology and nomenclature to help us derive some basic equations for calculating the power transmitted from a simple belt drive. Let's consider the analysis of belt drives, but in this lecture we're going to ignore any centripetal force effects. So let's consider the torque acting on the pulleys. Now we know from previous work that torque, capital T, is the force, F, multiplied by the radius, R. So considering our driving pulley A on the previous slide, shown here, the torque acting would be TT, tight side tension, multiplied by the radius of pulley A, and we subtract from that TS, also multiplied by the radius of pulley A. So back to our figure, we were to consider a section through here and consider the free body diagram of pulley A. We would have TT here, multiplied by radius RA, minus TS here, also multiplied by radius RA. All that's happened here is that we factorised on RA. And using the same approach, we can determine the torque acting on the driven pulley labelled as B in our sketch. That's simply the tight side tension multiplied by this time RB minus the slack side tension multiplied by RB. So again, we can factorise on RB. Again, note from previous work that the power transmitted, P, is the torque, T, multiplied by the angular velocity, usually symbol omega. P is equal to T omega. Analysis of the belt drives continued. Let's consider the belt linear velocity to angular velocity relationship we mentioned previously. Under normal loads with no slipping occurring, the linear velocity of both pulleys is the same, and it's equal to the belt velocity. Thus, given the angular velocity omega of the pulleys, and noting the linear relationship of V is equal to omega r we mentioned previously, then for pulley A, the linear velocity V is equal to omega A multiplied by RA, and for pulley B, the linear velocity V is omega B multiplied by RB. If we now equate the equations for linear velocity, VA equals to VB, then we can simply write omega A RA is equal to omega B RB. I've called that equation 1 just for reference. Analysis of belt drives continued. Just repeated equation 1 for reference. So from equation 1, we can rewrite angular velocity for pulley A, that's omega A, as V divided by RA. And we can write the angular velocity of pulley B, omega B, as V divided by RB. V is our belt speed in meters per second. So considering power generated from pulley A, remember power is torque multiplied by angular velocity. We know the torque on pulley A is Tt minus Ts multiplied by Ra, as stated here. And from above we can replace the omega A with V divided by Ra. We can now see that the Ra in the numerator is cancelled by the Ra in the denominator. So the power generated from pulley A is Tt minus Ts. That's the tight side minus the slack side tensions, now multiplied by the linear velocity V. So the power transmitted by a belt drive at low speeds, ignoring any centripetal forces or centrifugal effects, and noting that the linear velocity is the same for both pulleys, then the power, capital P here, can be written as Tt minus Ts multiplied by linear velocity V, and I've called that equation 2 for reference. Again, it's important to note that equation 2 relates to power generated at low speeds. Here are some other useful formulae that we'll refer to within this current lecture. Firstly, calculation of the span lengths, symbol S, if the pulley center distance C is known. Just for reference, here span length S, denoted in figure 2, and our center distance C. So span length S is given by this equation here, given without proof, and labelled equation 3 for reference. The equation requires the center distance C and the respective diameters of pulley A and B. Second equation given to us is for the pitch length of the belt, labelled L. Just note that the pitch line is a line that's internal within the thickness of the belt that does not change its length when the belt is in use. So illustration here for the belt pitch line for a flat belt shown here, red dashed line, and again the belt pitch line shown here on the V belt and on the rope belt. Again, the pitch length requires the center distance to be known and the diameter of the pulleys. Equation 4 for reference. And finally, the angle of overlap, theta, that's the contact angle, both pulley A and pulley B. Here's our pulley A, in this case the driver, and pulley B, the driven. So theta A is given by this equation, produces the angle in terms of degrees, called that equation 5, and theta B given by this equation, called that equation 6 for reference. So some useful equations there calculating various geometrical properties of our belt drive, and we'll refer to these within a later example. Let's consider initial belt tension. So initially, both sides of the belt are tensioned to experience T0. To determine the tension required, it's assumed that the belt material is elastic and thus obeys Hooke's law. Since the total belt length is assumed to remain constant, then the increase in length on the tight side is equal to the decrease in length on the slack side. So thus it follows that the increase in tension, delta T, on the tight side is equal to the decrease in tension, delta T, on the slack side. So if the tight side tension is T0, the initial tension, plus delta T, then the slack side tension is the initial tension T0 minus delta T. So rearranging the above equations for delta T, we find that Tt minus T0 is equal to T0 minus Ts. And then rearranging for T0, we simply add T0 to both sides of the equation and add Ts to both sides of the equation. We find the solution Tt plus Ts is equal to twice T0. Call that equation 7. Maximum belt tension. So the maximum belt tension, Tt, that can be withstood by the belt is calculated by the following formula related to maximum allowable belt tensile stress, sigma allowable, and the cross-sectional area of the belt labelled as A suffix belt. So maximum tension in the belt Tt is equal to the maximum allowable stress multiplied by the area of the belt. Record that equation 8 for reference. Let's consider example 1. A flat belt drive system consists of two parallel pulleys of diameter 100 mm and 150 mm, which are positioned 250 mm between centres. If the maximum belt tension is not to exceed 1.2 kilonewtons, the coefficient of friction between the belt and pulley is 0.4, and the larger pulley rotates at 290 rpm. We've got to calculate the following. Firstly, the speed of the smaller pulley. Secondly, the belt angle of lap for both pulleys. 3. The system power transmitted if the slack side tension is 40% of the tight side tension. 4. The initial belt tension required. 5. The pulley system span lengths between centres. And 6. The belt pitch length. The answers are shown in the bracket here. If you think you can attempt this question without further assistance, I'd encourage you to stop the presentation and do so, but the full work solution is shown on the following slides. Example 1. Here's the commencement of the solution. We extract the information from the question. Given in the question the diameter of the pulleys. So diameter 100 mm here. I've called that pulley B in this case. And 150 mm. Called that diameter A in this case. And the centre distance of the pulleys is 250 mm. So 250 mm shown here. We're given the maximum belt tension, 1.2 kilonewtons, so T max here is 1200 newtons. That'll be my TT value in my calculations. We are given the friction coefficient in the question, 0.4 between belt and pulley contact, but I don't think we'll be using that value in these calculations. We will have to consider the friction coefficient in future calculations. We're also informed the larger pulley rotates at 290 rpm. That's my omega A here, 290 rpm. I've also added on this slide the angular velocity calculation for pulley A in terms of radians per second. So this is omega A here. We simply multiply the angular velocity in RPM by 2 pi upon 60. So in this case, the angular velocity omega A is 30.4 radians per second to 1 decimal place. So now we've extracted the information from the question, we can begin the calculations. Example 1, solution continued. So first of all, we have to calculate the speed of pulley B. To calculate the speed of pulley B, that's omega B, I'm going to use equation 1. Basically divide both sides by radius of pulley B, and I'll find omega B. So that's the calculation here. Omega B is equal to omega A, speed of pulley A, multiplied by RA, the radius of pulley A, divided by the radius of pulley B. Inserting our values, that's 290 RPM for omega A. The radius of pulley A is actually 75 millimeters. I've written that in meters here. And the radius of pulley B is 50 millimeters. Again, I've written that in meters here. So the speed of pulley B is 435 res per minute, which I've also calculated in terms of radians per second for reference. Just note I have used meters in my calculation here. As I've said many times, I always use meters in dynamics calculations to avoid any conflict of units that might occur. But in this particular case, for this calculation, because we are considering ratios of speeds and radii, I could have used millimeters in the calculations. I would have calculated exactly the same speed. But I prefer to always use meters to avoid any potential unit conflicts that can occur in the calculations. Part 2, we've got to calculate the angles of lap for theta A, for pulley A and pulley B. So for pulley A, angle of lap is denoted as theta A. The formula was given on the previous slide, but we need to insert the diameter of pulley A into the formula. Again, I've used meters. And the diameter of pulley B. Again, I'm using meters. And the centre distance C is 250 millimeters in the question. Again, I've used 0.25 meters. Again, I could have used millimeters in this calculation. So evaluating the angle of lap on pulley A, theta A is 191.5 degrees. I've also calculated that in terms of radians as well here. We do not need the radians value in this particular example, but in later problems we will need to have our angles of lap in radians. So we've now calculated this angle of lap for pulley A. To calculate the angle of lap for pulley B, it's simply 360 degrees minus the angle of lap for pulley A. So theta B is 168.5 degrees, or again, it's been converted to radians here. And that's this angle of lap here. Example 1, solution continued. Now I've got to calculate the power transmitted, where P is equal to the maximum belt tension on the tight side minus the tension on the slack side, multiplied by the linear velocity V of the belt. So we know from the question that the tight side tension TT is 1200 newtons. We're given in the question a relationship between TT and TS. TS is actually 40% of TT. So that's 0.4 multiplied by 1200. So TS is 480 newtons. And to calculate the linear velocity V, we know that's omega multiplied by R. I'm using pulley A here. So the speed of pulley A in radians per second is 30.4 radians per second. And the radius of pulley A is 0.075 meters, 75 millimeters on a diagram here. So we can evaluate the linear velocity for the belt is 2.28 meters per second. So inserting our values into the equation, the power transmitted is 1642 watts, or approximately 1.64 kilowatts. Example 1, the solution continued. Part 4, we're asked to calculate the initial belt tension, T0. We're using equation 7 here, just dividing both sides by 2. So initial belt tension T0 is TT plus TS divided by 2. So TT plus TS divided by 2, inserting the values. The initial belt tension is 840 newtons. Next we're asked to calculate the pulley span length, that symbol S in our diagram here. Again, we're given a formula stated here. We just need to insert the center distance C, which is 250 millimeters on our diagram. I'm using meters again, so 0.25 meters here. And also the diameter of pulley A, diameter of pulley B. Again, I'm using meters in my calculations. So that evaluates to a span length of approximately 249 millimeters. Example 1, solution continued. And the final part of the problem, we're asked to calculate the belt pitch length. That's the length of the belt at the pitch line of the belt. And again, we're given a formula for pitch length L. Just need to insert the appropriate values for C, for pulley A diameter, and pulley B diameter. So evaluating L is 0.895 meters or 895 millimeters. So that concludes the solution for example 1. Example 2. In a flat belt drive, the tight side tension is designed to be 1.69 times the slack side tension. The small pulley diameter is 140 millimeters and rotates at 600 rpm. Ignoring centrifugal effects, we're asked to calculate the power that can be transmitted by this system. The belt allowable tensile stress is 2 megapascals and the belt section is 10 millimeters thick and 50 millimeters in width. Answer is shown in the bracket. If you think you can attempt example 2 without further assistance, I'd encourage you to stop the presentation and attempt it now, but I'll show the full work solution on the following slides. So example 2, solution. Subtracting the information from the question, we're initially given the relationship between the tight side and slack side tensions. We're informed that the tight side tension TT is 1.69 times the slack side tension TS. We're given the small pulley diameter in the question, capital D here, 140 millimeters, and I'll convert that straight away into meters, 0.14 meters. So the radius of the small pulley would be the diameter divided by 2, so 0.07 meters. We're given the belt dimensions in the question. Width B is 50 millimeters and depth D is 10 millimeters. That's the thickness of the belt. So we can calculate the area of the belt, simply B multiplied by D. So inserting the values, that evaluates to 0.0005 meters squared. We're given the belt allowable tensile stress of 2 megapascals. So sigma 2 megapascals, that's 2 times 10 to the 6 newtons per meter squared. Remember, a pascal is a newton per meter squared. And we're also given the angular velocity omega. We're told that the pulley rotates at 600 rpm. So converting rpm into radians per second, that's 20 pi radians per second for the exact value, or in decimal, it's approximately 62.83 radians per second. So here's the information extracted from the question and converted to appropriate units. Example 2, solution continued. The question wants us to find the power that can be transmitted P. So that's equation 2, derived previously. So we need to calculate the tight side tension, the slack side tension, and also the linear velocity V of the belt. So let's start by calculating the linear velocity of the belt, V. That's omega multiplied by R. The angular velocity of the pulley is 20 pi radians per second, and the pulley is 0.07 meters radius. So the linear belt velocity is 4.398 meters per second. Next, we'll calculate the maximum belt tension, TT. That would be the belt allowable tension multiplied by the area of the belt. We're given the allowable tension in the question. We calculated the area of the belt on the previous slide. So the maximum belt tension is 1000 newtons. We next need to calculate the slack side tension TS. We have a relationship between TT and TS. TT is 1.69 TS. Transposing the equation for TS, that's TT divided by 1.69. So TS evaluates to 591.72 newtons. And now we can find the power transmitted P by inserting the above values into this equation. So evaluating the power transmitted is 1796 watts, or approximately 1.8 kilowatts. And of course that's ignoring any centrifugal effects. So there's the solution for example 2. So that's the end of part 1 of the introduction to friction belt drives. This is the bibliography used to help generate the presentation, and I hope to see you in part 2, where we consider a further analysis of friction belt drives. I hope this has been of interest to you, and thank you for viewing.